Hey everyone, this is Dr. Walker. In this video, we're going to go over an example going over the general definition of electric flux learned in v514. In this example, we're finding the flux through a rectangular surface, but the electric field is not uniform. We can see that it varies along the y direction. Since this is the case, we know that we need to use our general definition of electric flux, which is the surface integral of E dot dA. So how do we use this equation? Well, first of all, the electric field is given to us, so we can just plug that in. C y squared in the k direction, the z direction. What about dA? So if you remember, dA is going to be a vector of magnitude dA, but the direction is going to be perpendicular to the dA, which is going to be in the direction of the unit vector, the normal vector perpendicular to the surface. And in this case, perpendicular to this horizontal surface, the n unit vector is going to be in the k direction or the z direction. So we need to figure out what is this dA. In general, the dA, we break up our surface into a bunch of very small patches. And we can definitely do that this time, and I'll show you how to do that. But in this picture, we can see that the dA has been given to us as a strip. So why is that? Well, because the field depends on the y direction. It doesn't depend on the x direction. So along the x direction, the field is constant. So if we pick our surface area element here to be a strip along the x direction, we're going to have a constant field. And that's the requirement for these little surface elements, that we need a constant field throughout the whole surface element. The advantage of picking the strip is that then we only need to integrate along the y direction here from 0 to a to get the contribution from all of these strips. So our surface element, area element dA, is going to be b, which is the length, times dy, which is the width, that very tiny width of that strip. So we can write b dy, and we said the unit vector is in the k direction. And we know that we're going to integrate y from 0 to a. Now we can go ahead and take out the constants that don't depend on y, c and b, and then we're going to have the integral of y squared dy, since k dot k is 1. And now we take our integral, we get cb y cubed over 3 from 0 to a, and when we go ahead and solve that, we put that 1/3 in front here, we're going to get cb a cubed minus 0 cubed. So this is our final answer for the flux, newtons meter squared per coulomb. That is our flux. Now, really quickly, what if you just didn't think of breaking it up into a strip? What if you just wanted to do the dA as a little patch? How would you do that? Well, that little patch here would have a width dy, just like the strip, but the length here would be dx. Right? This is a very small patch that has very infinitesimally small. So when you do the integral, you're actually going to have to integrate over the x and the y directions. You plug in your e, cy squared k hat, and then your dA isn't b dy anymore. The area of this is length times width is dx dy. But the direction is still in the k hat, the k direction. And we know that x integrates, that little patch we need to integrate from 0 to b, and in the y direction from 0 to a. So x is going to be from 0 to b, and y is going to be from 0 to a. So we can go ahead and do this. The c is constant, the y, that goes from 0 to a, we have y squared dy, and then for the x, that goes from 0 to b, we just have dx, right? And then k dot k is 1. And so you can see that we get the exact same result when we do this integral, that we get c, then this is going to be y cubed over 3. This is a 0 here, not a b. It looks like a b, but these are zeros. So this is going to be, this integral here is going to give us a cubed over 3, and this integral here is going to give us b. So we get the exact same result. So if you don't see to divide the area into a strip, you can still do it as a patch. It just requires 2 integrals instead of 1.